So welcome all to this new Continual AI online meetup. This is the April meetup, and in this meetup we're gonna talk about real-world applications of continual learning. And as always, this meetup will last around 90 minutes with four different spotlight presentations that will gonna last 15 minutes each, followed by 30 minutes discussion on the topic. So for this meetup, we have these four speakers. Maybe there's someone with the open mic. I can turn that off. Okay, right. So I was saying that we have four different speakers. So the first one is Tom Diety. I don't know if he's here, but he is going to talk about, he's from Amazon Research, and he's going to talk about continual learning in practice, a recent paper he presented. And then we're going to hear from Keval Doshi from the University of South Florida, talking about an application of continual learning to anomaly detection in surveillance videos. Then we will move to Lorenzo Pellegrini, talking about an Android application for continual object recognition at the edge. And finally, we will hear from Dani Kiyasseh from the University of Oxford, talking about CLOPS, continual learning application to physiological signals. Are you there, Tom? I don't think he's here. So maybe we can start directly with the presentation from Keval, hoping that Tom will join later. Keval, are you here?
Yeah, I'm here.
Cool, great. So maybe you can start your presentation. You can share your screen if you want, if you have some slides. Otherwise, you can just talk.
Yeah, I do have some slides, but could you please help me here? I'm not very familiar with Hangout. I'm not sure where I can.
Yeah, absolutely. So you can find the button on the bottom right of the interface, of the Google Meet interface, where you can find this button where it is written present now. And you can share your entire screen or just a window.
Unfortunately for me, on the bottom right, it's just showing turn on captions. Not getting.
Okay. So you can find on the right of the turn on captions the present now button.
No, I don't think I have that button.
Are you working with the Chrome browser?
Yep, the browser.
Well, that's very strange.
Let me do one thing. Let me join again. At that time, I think it asked me if I wanted to share my screen.
Okay,
so
let's try that.
Yeah, maybe that would work. Okay.
Great. Let's see if we can come back. All right. I can see your screen now, Keval, but I can't hear you.
Hey guys, are you
And
able
now
to
I
see my?
can. Now
Okay,
I
great.
can. I can hear you.
Sorry for the trouble. Okay, hello everyone. My name is Keval Doshi, and I'm a PhD student at the University of South Florida. And today I'm going to present my work on continual learning for anomaly detection in surveillance videos. So the outline for today's presentation is as follows. First, we will go over the problem definition and what are the main challenges which are faced in the existing systems. And then we will move on to our proposed approach and briefly go over some of the experiments that we have done, and finally concluding with some closing remarks. So, as we all know, the number of CCTV cameras have been increasing at an exponential rate. It is an essential tool with many applications in fields like law enforcement, intelligent transportation systems, among many others. And due to the massive amount of data that is being generated in real time, it has become nearly impossible for video monitoring to be done by a human operator. And there have been several works previously in the domain of automated video surveillance, but we believe that any real-time surveillance system which is practical and can be implemented in a real environment should be able to learn continuously from the data that it receives. And moving forward with that, these are some of the challenges which are faced by the existing systems. And the first one is that for a complex application such as video surveillance, it is very difficult to define what exactly is a nominal or anomalous behavior. Now, for example, let's take the case of a person who's running in the background or in a video. And this kind of behavior can be considered as nominal or anomalous depending on the situation and the context. So it gets very difficult to define what exactly is nominal or anomalous, which is the biggest challenge which we see in surveillance. Then the existing deep learning algorithms, which perform well, uh, they kind of fail to learn when it comes to continuously learning from the new data that it sees. So the key challenge with continual learning is to preserve the previously learned knowledge without accessing the previously seen data. And uh, in this particular domain, online decision making, which is real-time processing and real-time making some decision with a minimum delay, it's a very important but a neglected factor. So now I directly go over our proposed approach, and so as you can see, we have we are basically trying to reduce the use of deep learning models and use statistical models to continuously learn. Now, one main advantage that statistical models provide is that they give room for some performance analysis, which is really difficult to do when we work with just deep learning models. By performance analysis, I mean that coming up with bounds, error bounds on the false alarm period, error bounds for the detection delay, and having a statistical model here helped us to come up with these kind of bounds. So starting with the model, we use a pretty standard object detector model, YOLO, the version 3, which is really popular, and an optical flow model for uh, FlowNet 2. And our main thinking here was that uh, we wanted to monitor three main kinds of features. One, which was the appearance feature, was monitored by the object detector, which gave us the probabilities of what an object looked like. Then we were monitoring the trajectory of that particular object. So we were monitoring the center of the object along with the area of the bounding box. And apart from that, we were also monitoring the motion. So for motion, we considered optical flow, and we were extracting the mean, variance, skewness, and kurtosis, which are the higher order statistics from the optical flow. Now here's the continual learning part. So for this, from the feature vector that we extracted, we were actually using this feature vector to do continual learning. So we had proposed a sequential anomaly detection model, which was loosely based on the QSUM algorithm, but it is also non-parametric. So having a non-parametric algorithm in this domain really helped us, because it is almost impossible to know beforehand what kind of anomaly we might see. So that's why we went with a non-parametric algorithm. And so now here's how the algorithm works. So for each feature vector that we get, uh, the sequential anomaly detection model decides whether this particular feature vector is nominal or anomalous. If it is nominal, in that case, we just add it to our nominal training data. So this particular nominal training data consists of only features. So instead of storing the entire training videos or the entire videos that we have seen up till now, we just save these feature vectors, which consist of the important information that we have extracted from the videos. And from this particular nominal training data is used whenever we have to make some kind of a decision. And if this particular feature is considered as anomalous, in that case, we also propose a human in the loop kind of approach, in which during the beginning, a human decides whether this particular frame from which we extracted the feature vector is truly nominal or anomalous. Now, the reason for doing this is that sometimes when we do not have a lot of training data, and when we are dealing with tasks like surveillance detection in videos, a lot of the time we might see some behaviors which we have not seen before, but they are actually nominal. So if we do not, if we just consider it to be anomalous, then we might keep having those false alarms, as we'll see in some of the experiments. But having a human in the loop approach, it indirectly helped us to reduce those kind of false alarms, as we were able to differentiate between what's truly nominal and what's truly anomalous. So now here in the slide, we'll go over how the sequential anomaly detection model really helps us to reduce the number of false alarms. So as I said previously, we employed a non-parametric sequential anomaly detection algorithm, and it is loosely based on QSUM and k-nearest neighbors. And we asymptotically show that such an algorithm is able to minimize the detection delay while satisfying a given false alarm rate. So as you can see, without using a sequential anomaly detection model, the statistic which is given on the first figure, it is kind of noisy, and because of that, it also leads to some false alarms. But in such applications, we know that anomaly will be persistent and continue. and continuous, and it will go on for some time. So using that information, we are able to use a sequential algorithm, which is able to remove all these false alarms. And as you can see in the figure below, it's not very noisy. And using, since we are also using a statistical model, it is possible for us to come up with a formula to find out the exact threshold h, which we would need. So it's kind of a upper bound, sorry, a lower bound on the false alarm rate. And using that threshold, we are able to decide what should be uh, the threshold to have at max that false alarm rate. And so thus we are also able to reduce a lot of those false alarms that we see before. Now moving on to the experiments. The existing data sets that people have used before for anomaly detection and surveillance videos, particularly, are the UCSD pedestrian dataset, the Avenue dataset, and the Shanghai Tech dataset. Now, if you see, I'm not sure if it's very clearly visible, but if you see, there is a very clear distinction between the nominal and anomalous cases. So in the nominal case, usually there are just people walking, and in the anomalous case, uh, there's usually a person riding a bicycle or a cart going or a person running. Which is kind of really distinct. And in a real world application, we are not going to see something so distinct. So with this, we made some changes to the UCSD pedestrian dataset. So instead of just considering that any person moving using a bicycle is nominal, or sorry, using a bicycle is anomalous, and using a cart is also anomalous, we kind of segregated them into two different classes. So we said that anyone who's using a bicycle is, let's say that this is something that we encounter in the testing part, and it is actually nominal. So during the first time, yes, we do raise an alarm when we see such an incident. But with the human in the loop approach, the human says that no, this is actually nominal. So because of that, in the ongoing next test instances, we try to reduce or completely remove such false alarms occurring. And the rest of the anomalous occurrences, such as a car going or a person using a skateboard, is still considered as nominal. So we compared our algorithm with two of the most recent uh, video surveillance algorithms, and they do not really propose that they are able to do continuous learning. But in this particular domain, it was difficult to find any other work which was able to actually do continuous learning as well as video surveillance. So for that reason, we went with the two of the state-of-the-art algorithms for video surveillance, and we see that after a few, even after seeing just a few number of samples, our area under the curve, which is uh, uh, a common metric used in these applications to measure the performance, it increases considerably. So by the time that we are able to receive 25 uh, samples, our AUC is over zero point 0.8, which is uh, not that great, but it's still better than what the existing algorithms are able to achieve. Now, we also went with to show that our algorithm is actually able to learn continuously. We also went with a CCTV surveillance dataset, in which our main task was to learn previously unseen nominal behaviors. So we only started with about 10 minutes of data and 10 minutes of training data. And the total testing data went on for 8 hours for the same location. And this is kind of new in the literature, because most of the data sets, they only go on for about 10 to 15 minutes for a particular location. But in this case, it's the same location for 8 hours. So we wanted to show that our algorithm can work in a real time situation. And as you can see, just in one situation in 8 hours, the environment changes quite a lot. So we had uh, rains, and then there were some instances where people were walking across the street in a particular location which was not seen before in the training data. And there were also new type of vehicles such as bikes which were not previously seen. So uh, in the results, we show that this on the y-axis we have the false alarm rate, and on the x-axis we have the number of segments. So each segment here is about 25,000 frames, and we show in the first 20,000 frames, because of the rain, which was a change in the weather, we had some false alarms. So we are comparing with our own algorithm, but in the comparison, our algorithm is one part is performing continual learning, and the other one is not performing continual learning. So we see that when we are not actually performing continual learning, our false alarm rate is kind of really high, and we are not actually learning anything from the data that we are receiving. So in the first instance, when it was raining, uh, we uh, we have a false alarm rate of about 0.55, but after continually learning from the data that we have received, it reduces to 0.35. And even other instances, such as a person jaywalking or a person riding a bike. Uh, the first time a person riding a bike was seen was somewhere around in segment 18. But even after that, we saw many bikes coming and going in the later segments, about 25 and 23, where the non-continual learning algorithm has false alarms, but we do not. So this shows that we are actually able to learn continuously, whereas uh, whereas the same algorithm without the continual learning feature is not. So I think I'm running out of time, so I'll just conclude. And in this particular work, we propose a continual learning algorithm, which is able to use transfer learning for feature extraction and a statistical decision-making module. And the ability to continually learn and adapt to such new scenarios should significantly improve the current video surveillance capabilities. And in the future, we are planning to extend this continual learning framework so as to account for new anomalous labels and even other tasks such as updating our object detection model and even action recognition. So I think I'm done here. Thank you. And are we taking questions right now, or is it towards the end?
Thank you very much, Keval. I think that we can take just one or two punctual specific questions, if there are any doubts, and then we can move the discussion to the end of the meetup. We have
Okay,
plenty
great.
of time.
So any questions?
Maybe I have one.
Yeah, sure.
So essentially, in the continual learning part of this framework for surveillance, you store a number of embeddings, or let's say features they extract before, right? And you keep storing them over time. So is this a growing overhead over time in terms of memory computation? And do you think it will impact, your framework
Uh,
if this system is used, for a very long time for surveillance in a
Actually,
specific application?
that's a really good question. So I think you mean these
Yes.
features that we store.
Yes, exactly.
Yes. So yeah, if we continuously keep storing these features over a long period of time, yes, the computation is going to get a bit expensive, because in here we are computing the k-nearest neighbor distance for each feature to this training
Yeah.
data. So if this becomes too big, yes, the computational computation goes too high. But we also have a solution for that. So as you can if you think about it, a lot of these features are going to have a similar uh,
Yeah.
are going to be quite similar. So let's say that I'm monitoring this particular location. So if a person is walking, and then we see towards a few hours later another person walking.
Sorry, I can't hear you anymore.
Yeah, somebody muted me. I
Okay.
don't know.
Yeah,
Yeah.
please don't mute each other.
Uh, okay. So okay, I was saying that by using some kind of clustering techniques, we are able to reduce the computational complexity quite a lot, because a lot of these points now, this feature vector is computed for each frame. And if you look at a video of frames which are nearby are going to give up similar feature vectors. So there's no need for storing each and every one of them. So by using some clustering techniques, we can actually keep the computation size to a minimum.
Okay.
And uh, the memory issue shouldn't really be there, because the feature vector, the size of the feature vector in our application was about 19. And even if we store, let's say, for 100,000 of them, so it's still going to be 19 cross 100,000, which is going to end up being a few megabytes maybe.
Mhm.
So as compared to storing now 100,000 feature vectors would account for hours, literally hours of training data. So it would account for maybe 30 or 40 hours of training data. Now, so basically we are compressing, extracting those important information from 40 hours of training data to to a feature vector of megabits. So I think that should work well in the current setup.
Yeah. All right. So thank you again, Keval, for the nice
Thank
presentation.
you.
Maybe I will have a few questions for you later in the second part of the meetup. Now
Sure.
I've
Thank you.
seen that I've seen that Tom joined us. So maybe you can now, if you can, Keval, remove the presentation mode
Yeah,
from
sure.
yeah. Then maybe Tom, that is now here, can start with his presentation on continual learning practice.
Hi there. Yeah. So how do I do this?
So you should have on your screen on the bottom right a button.
Present now.
Present now, exactly.
Okay. Okay, can you see anything?
Yes, and hear it well.
Okay, great. First of all, thanks very much for the invitation. It's really cool to be here. And secondly, sorry for getting the timing wrong twice. So
No problem.
first of all, I got it a day wrong, thinking it was yesterday, and then I got it an hour wrong, thinking it was in an hour's time. So good start. I'm continually learning, shall I say?
Yeah.
Right. I mean, I guess like I have to kind of whiz through this. I'd love to talk in more detail about some of the things we're doing. This is kind of pretty high level, so I won't go into much technical detail. But I'm happy to talk more about things as well. I don't know if this. Right. So I mean, like, this is a bit of a cheat, really, to say continual learning at Amazon, and point of all the like ML things that we're doing. But I think the point is here is that there are many different places where machine learning is used, and I mean, I would say currently most of these don't have a so-called continual learning system backing them at the moment, but it's everyone's kind of desire that we should do, for reasons that you're probably all aware of. And so this is something that that within Amazon we've been starting to really like look into it more deeply. And so I can talk about like a little bit like, so I spent some time in the Alexa org. I guess everyone, oh, sorry, I maybe shouldn't say, I should say like her in the corner or something. If I just woken up a load of devices, I'm sorry. I think everyone knows pretty much what it is. But the question is like, how do you make a system that's robust and efficient? We also have to really care about privacy in this situation, and that means more than just adhering to GDPR and or COPPA or other sort of privacy regulations. This really means like doing the best we can at all stages in the process. And I think actually this is kind of an important thing for continual learning that isn't often thought about. Another question is kind of fairness, like with the data that is collected is inherently biased, because we're not doing targeted surveys to collect our data. We kind of like collect the data just naturally from whoever's using the devices, which means that you end up with more data from your heavy users. So we have to worry about that as well in our system. So I think like big picture, continual learning, we should think about these other things as well as just the standard things about catastrophic forgetting and ability to adapt to new tasks. So like I like to think about these failure modes and split them up into what we call unintentional and intentional failures. So unintentional ones are the ones that are typically worried about in continual learning. So this is like, okay, what happens if there's data set shift? We have limited memory, so we don't want we don't want algorithms that are just sort of like getting more and more memory hungry over time. How do we deal with like outliers or anomalies? But there is also like there are also these intentional failures, which are you might think of like adversaries in the system, or there's the sort of like classical things that we've seen in computer vision, for example, of people trying to fool ML systems. Okay, and this is basically all I'm saying here is that the world is changing, but most of the machine learning algorithms that are used in practice at the moment, certainly not all, but most, make this underlying assumption of stationarity in the system. So this is kind of the call to arms for machine learning. So a question is like Sage could solve the problem for us, and SageMaker solves a lot of problems. It's made like putting ML systems into production much more rapid. It's used extensively within Amazon, but in effect, you could actually argue that it could even make the problem worse, because you can end up with this what we call technical debt, which is this notion that the easier it is to put a system into production, the more people that are doing it, the harder it gets to manage those systems down the line, when we know that we're in these changing environments. Okay, so most of this I've said already. I will skip this. The approaches that we've been taking are mostly based around Bayesian continual learning. So just in a single slide, this was so this originally came out of this the group in the University of Cambridge, which is just down the road from our office in Amazon in Cambridge. And the idea here is that effectively you're treating this as a sequential Bayesian updating rule, where for each task you use the posterior that you have from the previous task as the prior for the new task. And by doing so, you get this kind of nice recursion, which allows for efficient algorithms. And we note that like the actual parameters theta here that we're looking at could be basically anything. So BLR is Bayesian linear regression or logistic regression. BNN is a Bayesian neural network where your theta are the network weights, or it could be a Gaussian process, for example. And this framework allows you to kind of mix and match models as well. However, I would say that what we have observed really is that, and I know this is one of the themes of the meetup, is that the continual learning algorithms that are out there are what we would say are not production ready. So we've kind of been we've been researching, and we've been working, and we've been writing papers on continual learning methods. But at the same time, we've been looking at this from an engineering perspective as well. And the question there is, like, how would you architect a system such that it is robust to these kind of settings? So we started looking at, like, okay, so what are the things that we're worried about, and what are the things that we would build in order to mitigate those problems. So some of the components here are like a sketcher or compressor, which is trying to help with memory issues. A kind of a joiner, which is allowing for the fact that you're in streaming settings that you might have different input sources coming in at different times. Labels might come in at want to make sense of all that. Ultimately, you'd like to have like a shared infrastructure where the data, the model, the parameters, the validation data, the training data from previous runs, everything is sort of stored in an intelligent way. The amount of space is partitioned nicely between them. And so you can kind of think about this in the way that a computer operating system works, that you don't really have to think about most of the stuff it's doing under the hood. But it's it's sort of like managing which things go in the cache and which things go in main memory and stuff like that. And then the other thing you want to have is a lot of kind of safeguards in there. So there's sort of like data monitoring. So this is more like on the input side, looking at can we detect if there's been some kind of shift in the input distribution? Can we detect anomalies and sort of flag ahead of time that our ML system might go wrong? We can also look at the output side. We can, even if you don't have labels yet, you can look at the stream of predictions that are being made and sort of say, okay, well, suddenly the predictions are outside of the normal quantile range that are expected for this model, and that can be flagged as an error. And then ultimately, you want some kind of policy engine. So this is an intelligent system in itself, really, whose job it is to look at these quality control metrics and say, okay, this looks like a dangerous moment for our algorithm. We should retrain at this point. We should select this data to retrain, et cetera, et cetera. Ultimately, the policy engine itself could be some form of reinforcement learning algorithm, but obviously then you need to kind of continually learn the policy engine. So you maybe start to get turtles all the way down or something at that point. So this is kind of everything I've just described in a single computational graph. This is something that we've built a couple of times now. It's still kind of rough, but this is sort of like how we think about like a continual learning system that's more than just like how do you deal with your neural network weights being updated. So just to summarize, like our are kind of, from a technical point, we kind of like the Bayesian approach. Doesn't necessarily mean it's we're wedded to it, but that's where we've done most of our research. It is tricky to make those work well with deep learning methods, but that's kind of been changing all the time. There's really exciting stuff going on there. But in general, like for most of the stuff that's out there, we would say that it's not production ready, and as long as it's not, you really need to combine it with some sort of engineering viewpoint. Okay, and I will stop there.
All right, so thank you very much, Tom, for your presentation. Are there any questions, specific questions we can ask Tom? Maybe I have one.
Sure.
So I don't know if you can share it, but I have seen that, I mean, a paper from Google that the paper was about TensorFlow extended. So this version of TensorFlow that apparently is being used behind some Google products like Google Play and others. And it was saying that they already integrated continuous training. This is what they call it, feature, where essentially you have a continuous integration system for serving new models that are being updated based on new data, of course, that the users are generating. And in this approach, they don't talk about complex continual learning approaches, but they talk about this work in it approach in which they just don't start again from scratch for training the model, but they just use the, let's say, the latest model as a place to start, and then they use just a part of the previous, let's say, data. They of course are accumulating inside their database. So it was interesting in understanding, if you can share it, if at Amazon, that this is being, is a, for example, an approach that is being undertaken apart from these possible Bayesian and future not production ready algorithms.
Yeah, sure. So I would say, like, the standard approach to solving the problem is, like, the most basic approach is just retrain on a fixed schedule and retrain from scratch, right? That's your most basic approach to the problem, and that probably is done by most teams in the company, and I would imagine the same is true of Google, right? I think that's probably the same everywhere. There are a lot of cases where it doesn't make any sense to retrain from scratch. If you're working with some gigantic transformer model or something like that with billions of parameters, you're not going to retrain that from scratch every time. But you have new data coming in, so for sure, there are teams that are doing sort of just like retraining, but retraining like fine tuning with some new data. It tends to even in that case, it tends to be like kind of rigid in the sense that this will happen whatever whatever's going on in the outside world. And then, like, we can think about a situation like, so suddenly everybody's working from home, shopping behavior on Amazon.com for sure is changing, and okay, does that existing method cope with that or not? And I think one of the like features of continual learning, that it's kind of this sort of plasticity in a way, the ability to adapt to the speed of changes in the outside world that's interesting. So, like, in an ideal situation, if nothing was changing and your model was doing fine, you wouldn't really touch it. Like why would you? Unless there's something really new, then then like you'd be better off leaving it on compute cost by doing so. But then other times things are changing, and if you're stuck with a like I only train every week, you know, you might be missing a load of stuff in the middle of the week because things have changed too fast. So it would be really advantageous to then move to a more flexible schedule where you're retraining when things are changing faster, and not when they're moving slower. One of the like weird issues about that is that it's kind of hard to reserve compute infrastructure in that way, in a flexible way, because if you say, okay, I want a whole bunch of P3 machines to be available for training. Okay, you have like auto scaling up and down and things like that. But if you think about like the data center, if everybody's on the same schedule and they're all affected by the same outside issues, then that you could run into problems there.
Yeah. Okay, so essentially you're saying that most of the innovation in continual learning should be about being able to detect when the change is happening in the world and react, let's say, accordingly.
Yeah. I mean, I kind of see it a bit more like you've got your machine learning system. It's kind of like I think of it like a layer over the top of it, it's almost like an intelligent like management layer, whose job it is to work out when this thing is likely to be going wrong and do something about it. I mean, you could call it the same system. It's like whether you differentiate or not is.
Yeah, absolutely. All right, so maybe we should move on as the time is running. But Tom, of course, if you want to hang around, I think that many of us we will ask you more questions in the second part of the meetup, where we will open a discussion about this topic.
Great. Yeah, I'll stay on. Yeah.
Cool. So Lorenzo, are you ready? Can you share your screen and start with your presentation?
Yep. Okay, can you see it?
Not yet.
Okay. Okay, let's try it again. Can you see it?
Yes, now we can.
Okay. Thank you, Vincenzo, for the invitation. My name is Lorenzo Pellegrini, and I am a PhD student at University of Bologna. And my main research topic is continual learning, and I'm currently working on continual learning applications for edge devices. And today I'm going to show you the continual object recognition Android app I've been working on in the last year. The presentation will be divided in 3 parts. In the first part, I will just expose the motivation and the goals that led to the creation of the app. In the second part, I'll show you a short video clip, a trailer of the app, and I will describe some design choice we made. And at the end of the presentation, I'll try to describe some technical details about the app in a, best effort manner. It will depend on the remaining time I have. So let's start talking about motivation and goals. So the main motivation, when I first started developing the app, like 1 year ago, roughly, we wanted to demonstrate the potential of continual learning by solving a simple computer vision problem. So we just defined some clear goals, and we wanted this application to be widely usable, simple to use, tackle a simple yet realistic problem for edge devices. In those kind of devices where we don't have the same horsepower of a GPU-powered server, we have some constraints regarding CPU power, working memory, persistent memory, and even battery sometimes, and we may not have a stable internet connection. So we have to use the onboard hardware to complete the continual learning steps without um, without having to use cloud computing or some delayed computation elsewhere. So the app had to operate in a realistic environment, solve a simple yet realistic problem, had to run in common devices. So we choose Android smartphone as our reference platforms, had to be light on resources, and also had to use no internet connection at all. So this app works completely offline, both in inference and in training mode. And finally, no neural accelerators or custom hardware is needed. You just need your Android phone to run it. So it's a computer vision application. It solves a classification problem and learns from a video stream where the user is expected to put an object in front of his or her camera and just film using the app the object in front of it. And the app will classify it just in inference mode, or the user must be able also to increase existing knowledge for existing categories, or even add a fresh new object category. And this is this is completely offline. And in fact, the app is pretty much light on resources. You can run it also on a low-end smartphone, and you, of course, will get better performances on higher-end smartphone. But this is pretty much obvious. Um, so, as the name suggests, the app is strictly tied to the Core 50 dataset. For whom may not have already seen it, this is a dataset made of video streams. It features 50 different objects of 10 categories, and for each object we have 11 video sessions depicting the object in different backgrounds, poses, with different occlusions. The thing is that this dataset was recorded by the point of view of the user, and the user moves the object around by rotating it, and sometimes the hand of the user even partially abstracts it. And we wanted for the app to get the same amount of freedom we see in the Core 50 dataset. So this is a pretty much realistic scenario, and this dataset is even good as a good benchmark for robotic vision applications, and we wanted the same thing for the app. And the app, of course, will learn from video streams. So the best thing is to show you how the app works in practice. So I prepared a small video clip with my colleagues at the Machine Intelligence Laboratory. So let's see. Nope, nope, nope. Sorry. Okay, there is a link in the slides I'll upload later in SlideShare. Okay, nice. You'll be able to watch it on YouTube, and you'll also be able to download it. So the app starts in inference mode, and it comes with a pre-trained model on Core 50. And let's see how it works. Okay, this is the inference mode. The app starts in inference mode, and you have 10 initial categories, the core 50 ones, and the app user interface is divided in two parts. The bottom part of the app features the 10 different thumbnails for one for each category, and 5 empty slots at the bottom of it. The user will use those empty slots to add new categories. For around each different category may appear this green frame, which is a frame, it's just a graphical hint that this is the the category with the higher confidence score for the model. But you can also see here circular in red, a numeric score for the top 3 classes. You can also see in the upper part of the application, we have a frame per seconds counter. This is an old version of the app. In fact, the last version, the one you'll be able to download, is even faster than this. And in the upper part of the application, we have a central square, which will be the one actually considered when running classification. We wanted to not to tackle a detection problem, just a classification problem. This is why we restricted the area that which is taken into consideration, while leaving a grayed out area which is still transparent and will allow the user to better align, to more easily align the object inside the central frame. Okay, this is not really much about continual learning. In fact, this is a basic usage. And let's see how it works in the first continual learning scenario, which is the new instance scenario in which we want to improve model knowledge for an existing class. Okay, in this case, we have a plug adapter. This plug adapter get recognized, in fact, was in the training set, so we get in the most easier situation. But then we tried to show the app a plug adapter which was not in the training data set and in fact is black, it's strange, doesn't get recognized with accuracy. We want to improve the plug adapter category, so we put the object in front of the camera and we start gathering some frames. We only use 100 frames for training, so they are not very much, and they're taken at 5 frame per second, roughly 20 seconds. This. And at the end of the image gathering phase, the training phase starts, and in this old version of the app, it takes a few seconds, but in fact, in the latest version, it takes less than 1 second. As you can see, the app kept the existing knowledge for previous plug adapters and is able to recognize the new plug adapter as well. Now, this is the second use case. We are going to add a new category, a new class scenario. And first, I'll show you how the app behaves with mobile phone. Okay, and then we just show the app an object that was not in the original tag categories that get recognized uh, as a mobile phone. So we are adding a stapler here in the same exact way we did in the previous scenario. So is the exact same thing, but instead of improving the knowledge for existing classes, we are adding a fresh new class. We still use 100 different patterns. And here is very important to rotate the object, move it around, partially abstract it in order to improve the overall training quality. And as you can see, not only we can correctly classify the original stapler, we can classify with good accuracy another stapler, and most importantly, the mobile phone is still classified correctly. Okay. Okay, you'll find the YouTube trailer link here in the slides. I'll upload later and then post on both the discussion forum and Slack of Continual AI. Okay, I'll try to explain some technical details. I won't be able to explain exactly everything because of time constraints. The app is packaged with a custom Graph framework. The algorithm is written in C++, not Python, and uses a MobileNet version 1, retrained on ImageNet, and then fine-tuned on the first 10 categories of Core 50. The training is completed in just a few seconds, and in fact, in the latest version of the app, in a mid-tier smartphone, it completes in less than 1 second. But there is a trick in which we actually start training while the image gathering phase is already taken taking place. And as I told you before, we only use 100 frames, which is not that much, in fact, if you think about the complexity of the scenario here. And the but the worst part of it is that by using a video frame, you have only patterns from a certain category, maybe a new category, maybe an existing category. We only see patterns from a certain category. And this means that for the other category, we have no patterns, and this may lead to catastrophic forgetting. And in order to prevent this, we are running some we are using a rehearsal buffer that, however, for edge devices is has some good and also some bad and also some ugly aspects. Okay, rehearsal is good at preventing catastrophic forgetting, especially if you have a training batch with only patterns from a certain class, but is bad in terms that in training times terms. For edge devices, we don't have much CPU power. So adding a rehearsal buffer and inserting it in the overall training buffer for that step may increase the overall training time. And this is really bad if you want a very responsive app, and it may make the whole process to explode from few seconds to different minutes depending on the size of the rehearsal buffer. And the ugly part is that we have actually to store those rehearsal patterns somewhere inside the phone memory. And this means that, okay, it's not bad, it's just ugly because, okay, we store some kind of data inside the internal memory of the smartphone, but modern smartphones have a lot of memory. So this is just ugly, not particularly bad. The bad part is that training times explode. So this is while we, yeah, we want to keep the good part of it, we just don't want the bad or ugly part of it, or we want to limit the bad and ugly part of pure rehearsal. So instead of using pure rehearsal, we use latent rehearsal. We propose in our recent paper that there is this problem by storing not the raw patterns, not the raw training patterns, but it just stores some latent activation up to one certain latent replay layer. And in fact, it's very simple. It's a very simple mechanism. We just store latent activation up to a certain layer, and when a new training batch becomes available because the user prompted for a new training session, we run the classical flow from the input layer towards the output layer. But when the forward flow arrives at the latent replay layer, we merge it with the latent reaction memory, and then for the upper part of the net, we just run the classical forward and backward and update steps. And if you will have a look at the paper I linked in the final slides, you'll see that you can also employ some slow learning mechanism for the lower part, the feature extraction part of the net, but you can both freeze it or slow learn it. No matter what, you have to consider that when moving the lower part of the net and using this strategy, the latent reaction memory patterns may suffer from aging, of course, because the feature extraction part changes during time. And for the final fully connected layer of the net, use copy weight and reinitialize. You also find in the linked paper, and it's simple, it's very efficient, and most importantly, is very light on resources, and it's just applied to the last fully connected layer of the net. For any technical details, I think I'm running out of time, but for any technical details, I just left two references from our previous paper from my working group, and there is also the great Vincenzo Monaco Medium post. You can have a look at that will explain the app and technical details in less technical manner. And of course, there is the download link for the app. just a disclaimer, there is no source code yet. We are planning on releasing it after we complete our paper we are working on, and after this paper will be published, I'll publish the source code. Also because, well, the code is actually needs some major refactoring then tidy up, and in the meantime, you'll be able to download and manually install the APK for your device. And the only hardware requirement as of now is having a modern smartphone with a modern processor supporting the RAM version 8 instructions. Okay, that's it.
Thank you very much, Lorenzo, for your presentation. Does anyone have some questions about this presentation?
May I ask one? Yeah, my name is Igor. Thank you, Lorenzo. Very impressive. Nice to hear that. I saw just maybe it's not related to your topic, but your model is still trying to predict one category of data set when it sees unknown object. Is there any way, ideas how to make it more robust for the adversarial attack? I mean, just when it sees a new category, new object, it says, okay, I don't know. So it's self-assess in some way. So I don't know what I'm looking at.
Yeah, we are we are using the strong supervision signal from the user. So the app at the moment is not able to detect if the object is looking at is an object from an existing category, or if it's even tricked to think that this object is from another category. So yeah, we are completely user supervision dependent at this time. I think there may be ways to detect some kind of adversarial attacks, but as of now, this is really difficult, and maybe perhaps we can employ some kind of adversarial attack when dealing with detection mechanism, when the app will evolve in a further second step. But as of now, we wanted it to be simple, so the users is just the one who decides what each object really is.
Understood. Thanks.
Great. So just a reminder, we will start a topic on our discourse forum about this meetup. So I ask all the authors of these presentations to upload, the links to their slides, or at least put the references that you talked about on this discourse thread. Then I think we can move on to the next presentation from Dani. Kiyasseh. Did I pronounce that right?
Yep. I'm just going to pull up the slides real quick. Can you guys see them okay?
Yes, we can. Thanks.
Great. So thank you for all the presentations so far and for inviting me to speak. So I'll be talking about CLOPS today, which is the continual learning of physiological signals. My name's Dani. I'm a PhD student at the University of Oxford, and this is work with Ting-Ting Zhu and David Clifton here at University of Oxford. So to get started, this is the pathway that we'll be talking about today. We'll look at some of the current challenges, which most of you are familiar with, how it's currently solved, how CLOPS is different, the particular data set that we're using, or the family of data sets. We'll essentially see that CLOPS is a replay-based method. And so we'll talk a lot about a buffer, how to acquire, how to store instances into a buffer and how to acquire them from a buffer. And then finally, some results and the broader impact of our work will be explained. So just to start off, within the healthcare industry, data are collected using a diverse array of medical devices, be that wearable sensors, imaging devices, and so forth, from different patient demographics, whether you're young or old, and different comorbidities and so forth throughout the year. So that implies that there's a temporal component to the data that's being collected and at different hospital sites. And so you can quickly see that this becomes quite intractable in terms of the spatial and temporal components of the issue we're dealing with. And ultimately, all of these variables lead to distribution shift, which violates this assumption of independent and identically distributed data sets, which is an ultimate Achilles heel, so to speak, for deep learning algorithms. How do they currently overcome these challenges? This is not an exhaustive list, but I think, similar to what Tom and Lorenzo had mentioned earlier, you can evaluate this model under distribution shift. So for example, in the context of healthcare, you can train on hospital A, so train on data from hospital A and evaluate on data in hospital B, and kind of get a retrospective view of how your algorithm is performing. Unfortunately, though, this does not incorporate new information during training, so you're not really updating the weights in any way. The other way that is more direct to what has been mentioned is that you retrain the model with the entire data set. So this can be this is more akin to multitask learning, where you incorporate all the data from the past, for instance, and train on this much larger cohort, so to speak. And this issue, in addition to all the issues that have been mentioned, I think in healthcare it's more prominent because you have these privacy concerns with regards to patient health. The fact that past data may not be available, either because it was discarded or stored elsewhere. And of course, this approach does not really scale well. As you start to get more and more data points, it's just impossible to just store them all, or less tractable. So this is where we introduce CLOPS, and in one line, it's essentially a healthcare-specific, replay-based continual learning approach that is anchored around two basic ideas. The first is importance-guided storage, and the second is uncertainty-based acquisition. So just to remind you all, we're talking about a replay-based method, which implies that there's going to be a buffer, and so the question is, how do we store into this buffer, and how do we acquire from a buffer? There's a lot of work in this space, and so we appreciate that that's been done, and so we're just going to show you how we're slightly different from what's already been done. So let's talk about the first point here, which is importance-guided storage. How do we go about doing that? We need to determine which instances are important. To do so, we introduce something called task instance parameters, which we denote by beta. And they're essentially parameters that are introduced for each instance in each task. So for example, if you have 5 sequential tasks, each with 1,000 instances each, that's a total of 5,000 task instance parameters that are learned in an end-to-end manner during training. So let's say you're talking about a classification on or a regression on a particular task T. I don't know if you guys can see my mouse, but essentially you have LIT, which is the loss at the particular instance I on task T. If you're doing classification, that could be cross entropy loss or whatever you may like. All we're doing is weighting that loss by this term beta IT. So we like to think of this as some sort of attention mechanism that is placed on the output, on the loss for a particular instance. Now, if we were to perform stochastic gradient descent on this particular objective function, you'd immediately see that the beta values, whatever they were initialized to, soon start to decrease. They start to decrease and tend towards 0. And as a result of that, you'll end up not learning significantly from these instances. In other words, as the coefficient goes to 0, your loss is 0, and so you don't end up learning. To avoid that behavior, we just introduced a regularization term that says, okay, please keep this beta value close to 1, but do not constrain it too much such that you're still able to have sufficient amount of attention on these loss terms. This will become slightly clearer as we move forward. And so we kind of interpret these task instance parameters as the importance or difficulty of a particular instance throughout the training procedure. These are for the current task instances. As we eventually talk about how to acquire instances from a buffer, these are going to be from previous tasks, and incorporating them into the objective function is, as per normal, you just have a typical cross entropy loss. The one thing I would note here is that we're not introducing these task instance parameters beta for these in this replay loss. And maybe to clarify some terms here, I is the instance, B, large B, is the batch size, and then B subscript T is the batch size for that particular task. And so our objective function ultimately when we're training is just a combination of this current loss and the replay loss. So task instance parameters have a dual role. The first is, as we've shown here, these loss weighting mechanism. The second is its role for guiding the storage of instances into a buffer. And this is how we do it. We ultimately track the task instance parameters over time. So if you're training, for example, tau in this case is, let's say 40. So you're training for 40 epochs. You track these task instance parameters for 40 epochs, hence its dependence on time. So beta as a function of time. And you'd perform the trapezoidal rule with regards to those task instance parameters for each instance in that. So you're essentially just taking the area under the curve of the trajectory of these parameters and getting this value called S. Let's call it the score for instance. So each instance is going to have this store value. We will then sort these instances according to these score values in descending order and acquire the top B% of them and store them into this buffer that we're interested in. This is a buffer of finite size, and so we can play around with the size of interest depending on our computational constraints and so forth. So now that we've established how to store, let's talk about how to acquire from this buffer. And I think just to take a small interlude, this method is based on active learning and how it acquires instances using an uncertainty-based acquisition function, so to speak. We'll be using something called Monte Carlo dropout, variational dropout. I'll do a quick overview here just in case people aren't familiar with it. If you have a network with 2 layers, you introduce an input, you get a hidden layer and some posterior distribution. What Monte Carlo dropout does is apply a stochastic binary mask, which changes that posterior distribution slightly. You do this several times, and you ultimately end up with a matrix, which is T by C, which is the number of Monte Carlo samples that you've performed by dimension classes, which is the number of classes in your classification task, for instance. You then use this matrix that is available for each instance in your buffer to calculate an acquisition function of interest, which I show here. So a common one that is used is BALD. It just stands for Bayesian Active Learning by Disagreement. It was introduced by Yaron Gal and others. Essentially just looks at the Jensen-Shannon divergence between these posterior distributions. Very, at a high level, it's looking at disagreements in classifications across a bunch of different decision boundaries. And that is what that's ultimately looking for, hence the name uncertainty-based. So we're storing instances into a buffer based on these task instance parameters beta. Great. We're now acquiring instances based on this acquisition function, which we're calling BALD, Monte Carlo dropout, which is quite common to use. And that's how we'll go about doing this entire process. Because this is focused on healthcare, actually what we're looking at is physiological signals. We're looking at something called the Electrocardiogram Ecg or EKG, and it measures the electrical activity of the heart. This is what a standard ECG looks like. And abnormalities that will occur in the heart will typically manifest as abnormalities in the ECG. So this image here will get stretched and pulled. You get different amplitudes and so forth, depending on the abnormality that a patient experiences. So this is what we're feeding into our network and attempting to learn in a continual manner. Let's move on to what some of our results have generated. So if I direct your attention to the figure on the left, what we're showing you here is the area under the receiver operating characteristic curve as a function of the number of epochs during training. And we're showing you the validation set AUC. And then the one on the left is without any continual learning strategy. It's a simple fine-tuning strategy. And what you'll see is as you start to train on mutually exclusive pairs of classes, in this class incremental learning setting, there's this good amount of, let's call it, destructive interference that takes place. And you can see that by this, rapid drop in performance as soon as you start training on a new class pair. And so if we look on the right-hand side, this is where CLOPS comes into play, where we're implementing this replay-based method. As we're training on these subsequent classes that we have never seen before, we start to acquire instances from the replay buffer. And although we do see some destructive interference, it's definitely mitigated relative to the non-continual learning scenario. And so, more results are shown in the paper, but just for the interest of time, I've showed you these here. And then corresponding to these results, we'll show you what these task parameters actually look like after they've been trained. And so here I'm showing their distribution once they've all been trained for all instances, and they're color-coded based on the class, or let's say task, that they correspond to. The values that are lowest should be indicative of those instances that are hardest to classify by the network. And conversely, those that are highest in values should be those that are easiest to classify. And maybe, if you're not an expert in this domain, the one on the right is normal sinus rhythm, which is what your heart should look like. And that is expected. These are the relatively easy samples. On the other end of the spectrum, the ground truth label is normal sinus rhythm. But in reality, with a trained eye, you can actually detect certain abnormalities here, which should classify this as something which is not normal sinus rhythm, such as myocardial infarction and so forth. And so in reality, the algorithm was able to find instances that have been difficult to classify and potentially incorrectly labeled as normal sinus rhythm. And this kind of validates our use of these task instance parameters. And although we don't go into depth in this paper, we do kind of see the promise of these parameters as being used to quantify task similarity. In other words, how can we potentially fit a Gaussian to these distributions, compare them, and ultimately use that information either for forward transfer or potentially transfer learning down the line. All in all, I think this work does have a broader impact, especially since the intersection of continual learning and healthcare is relatively underdeveloped in terms of clinical adoption. As you have dynamically reliable networks, those that can perform well over time, that ultimately increases their trustworthiness amongst physicians and thus increases their likelihood of being adopted clinically. And lastly, the US Food and Drug Administration came out last year with a white paper talking about how to best move forward with regards to the adaptation of algorithms in an online manner. But I think as a community, as we start to explore these things better, we can start to play a role in policymaking to avoid the detrimental issues that may arise from not considering continual learning. But that's all I have for you guys today. Thank you.
Thank you so much for the presentation, Dani. Do you guys have some questions for this presentation? So maybe I have one fundamental question about the essentially the needs of storing data in a continual learning approach, especially in this domain of F domain. So do you think that we actually need to store some examples, some data, or replay in this case, for using continual learning in these particular scenarios? Do you think that we actually still have to store all these, private and data in general? I mean, for health, and or do you think that we should move as a continual learning, approaches in this area on a complete, version-free approaches?
Yeah, I think that's a good question. I think there are recent papers that came out recently that showed that replay-based methods are on average superior to, for example, regularization-based or dynamic architecture-based and so forth. And so that's kind of my motivation for going down that path. But ideally, yes, if we can move away from having to store large amounts of data, especially those in the raw input domain, would make it easier to overcome the challenges of privacy and so forth. Despite the fact that the data that we're working with here is really, de-anonymized or anonymized and hard to trace back to a particular patient, but I can see this issue arising in the broader domain of healthcare for sure.
Yeah, what I was thinking is that maybe you still need to, in the end, still need to store these data and not to delete them. I mean, because maybe you will need these clinical data of a particular patient in the future. So I was trying to understand the boundary here to say, okay, I still have to store these data because I will need them for other uses maybe. And it is important for a patient health, but at the same time, for continual learning approach, maybe you want to move to another direction, not storing them for privacy or other things. I don't know if I made it clear.
Yeah, no, that's a good point. I think, right, and I think there's a lot, more thought needs to be given about that process, and it is much more complicated. And just touching upon what Tom had mentioned earlier, I think that one thing is research, and another is a completely different world to kind of apply this in the hospital on a day-to-day basis. So that would require proper, an engineering perspective to kind of implement this, and hopefully we can do that as time passes.
Cool. So thank you again for your presentation. So guys, maybe we can move to open a discussion about these topics. I put a thing on Slack, a few questions maybe we can tackle. If you don't have, of course, other questions to the speakers.
Actually, so Tom here. I think it was a really interesting talk, Dani. I like that. I think touching on the sort of like the healthcare side of things. Do you feel like there's a potential issue if you have models that you're trying to give to medical practitioners to use, that they might inherently trust the system less if they don't really understand the training procedure, or is this something that you've considered in your work at all?
So you're saying if they do know the underlying workings, they may trust the algorithm less?
No, the other way around, actually. It's, being
Okay.
I guess in certain settings, people are very keen on. I mean, it's sort of like machine learning can be a leap already, because
Right.
it's not something you can like verify the code. If you think of like a the software that is used in the aviation domain, for example, it's seriously hardened and tested to the nth degree. So putting a machine learning system in there is probably it's a long way off reality. But and then a continual learning system where there's even less control, so to speak, of what the system is doing.
Mm-hmm.
In these kind of like mission critical settings, like a medical setting, do you feel that like trust in the system is going to be an issue there?
I think trust will always be an issue, and I think in this domain, this notion of whether it's a cliche or not, this human in the loop approach is a must in order to ensure that physicians are on board. But I think I was also on a particular call last week with Andrew Ng, and he was just saying the physicians that he's working with, yes, he does face this lack of trust at first, but in reality, the performance of the algorithms in the early stages, if they're sufficient, that can be enough to win over the trust of these physicians early on, such that the interpretability component becomes less integral down the line. Is that kind
right?
of
Yeah, that makes sense. Yeah, but I mean, I guess in a continual learning system, they probably also want guarantees about the future performance of the system as well.
Right, right. And that's not research that I've done yet, but it's definitely exciting future avenues that I'd hope to be involved with. Yep.
Cool, thanks.
Mm-hmm.
Yeah, maybe you guys touched on an interesting issue, because the question I wanted to ask you all actually was if continual learning is nowadays ready for real-world production environments. This is something that Tom explained before, maybe. But I mean, I still think that the reasonably well-behaving, let's say, strategies that we came up as a community in this field can be used today in a production environment. The problem maybe is more about do we as management of these businesses want to have that, in the sense that we risk to lose a bit of control over a model that normally would take like at least a team to train it, control it in terms of the evaluation, and then release it manually, or at least as fast as possible, but in a very controlled way. So do you think, guys, that this is the main problem? It's not about like let's say algorithmic problem of continual learning. It's more about study the impact of continual learning on the real world. That's the main issue.
But I think maybe a more general discussion is about the trust to the machine learning. I like how the one woman, Keyasseh Kozarkov, is famous Google engineer. She says about in the first place, we don't have to trust people because we don't know how the brain works. Okay, it's a black box. Okay, but there is a difference. We know how humans fail. Okay, we know, and we still don't know how our machine learning models fail. So once we will understand how and what are the limits of our, what are the failures of our machine learning models, the trust will come naturally, because you know how that may fail. And I like this this approach to this particular problem of trust.
Also, I think that at the moment as someone else told already, we practically use control of the model once your application gets released in the wild. I think that at the moment we still need strong supervision from the user to make things work for continual learning, and that's for sure. And I think that we still don't have some kind of silver bullet to use in real world applications, because for each context, for each scenario, and each platform, we may mandate to use different algorithms, more light algorithms or heavier algorithms. We may have access to GPU, memory, etc., etc. But in the very first place, very first continual learning applications will need strong user supervision. And I don't think we are already ready to release a standalone continual learning application without any kind of supervision from the user.
Yeah, so there was a paper from some Google guys a few years back. It was called "What's Your ML Test Score?" Have you seen that one? A rubric for ML production systems. And it's not really talking about continual learning as such, but it's more like the general problem of putting ML systems into production. I think you could like layer on some stuff about continual learning systems, and it's something we looked at when we started this research direction. And a lot of it about is what are the kind of right testing framework, what's the appropriate like level of monitoring that you need, and how do you how do you stop ensure that there aren't regressions when you put new models into production? So it's sort of like builds heavily a lot on what software engineers have been doing for many years, but sort of adapting it to this new world of like flexible code, I guess you could call it. Machine learning models are in a way are systems that are creating their own code.
Yeah, if I could chime in here, my understanding of the whole explainability aspect is that you have a much deeper evaluation method, basically a much more detailed one. Of course, that can become easily an overload, and especially those explainability methods that are about decision analysis, where you try to see like, why are you getting wrong predictions all of a sudden? But there's also this area of interpretability where you peer inside your model basically, and you kind of can understand whether it's making sensible abstractions, things like that. And I think that down the line might be much more interesting for continual learning. So we have done a bit of work on that for like standard transfer learning settings in NLP, and then applied that to a hospital data set for mortality prediction, and then having both this like explainability where you explain your predictions somehow, and like, it shows you what patient feature was responsible for a patient dying in the next 48 hours, this sort of thing. But also like understanding what the parts of your model learn, and which parts of the model and which parts of the data inputs you have connected give you the performance. Like you literally get this chart of like, okay, for this task, this data is the most important, and maybe this and this pooling mechanism in your model really matters. And I think for continual learning, I mean, we haven't done that yet because it's huge work, and ideally you want to get funding to actually do that in a hospital. Otherwise, where do you get the data from realistically? I think there's a huge gain in terms of that, not just in terms of trust, but it's also quite educational to see how the model makes predictions, and then to discover things that you didn't even think of. For example, one thing that we did is in the last paper is we took this data set where people used expert knowledge to pre-select feature to predict patient mortality and things like that, like ICU predictions, basically, right? And then we found out that they used like 100 features altogether, more or less, and then we just used all the features, which was 10,000, and we found out that we could double the performance with a model that was tiny in comparison. So we threw away transformers and just did a very simple, like almost non-CNN-like version of things. And it turned out that not only did the performance go up, but we could also peer into each individual like filter and kind of see, okay, this one is learning pain features, this one is learning blood pressure, this one is learning breathing, this one is learning whether patients can move by themselves, these kinds of things. And I think it's really important to kind of gain an understanding what the models are doing beyond just like the scores, because then once you do continual learning and like you do more and attach more data and all that, you kind of also want to see how that changes, like, how the model understands the yeah, that's it.
Yeah, absolutely.
I mean, maybe asking Dani, Dani, have you started with like, working with hospitals and getting that sort of data, and like really like, start working on that? Because I mean, public data sets are nice, but you always have to sort of construct a continual setup or something like that.
So all the data sets that I've used for the paper are publicly available. And I think the beauty of working with ECG data sets is that they're quite large, and they're increasing in size and diversity, those that are online. But to answer your question about private collaboration, and we do have the Oxford University hospitals here that are in tight collaboration with our lab. And so that is, we haven't collaborated with them particularly for the continual learning setting, but definitely on other projects though.
Okay, interesting.
All right, guys. I think we moved way out of the ending time for this meetup, but it was fun. So thank you all for joining and contributing to these discussions. I mean, we can keep them going on the forum of ContinualAI, so you're all invited to search for this topic, real-world applications of continual learning, and you can put there your material, your references, your ideas, and we can keep chatting. So thank you all for joining again. We have on Friday our reading group if you're interested. Not clear yet what we're going to read together, but if you have an idea you want to read a paper together, just send me a direct message. We can decide. Thank you again. So you will find this recording in the next few days. Thank you, guys. Bye.
Thank you.
Thank you.
Bye.
Bye. Bye-bye.
Bye.
Thank you. Bye.